Okay, welcome everybody to our very last session for today. We'll have 3 short talks in a row right now. And please welcome our first speakers, Enrico and Sebastian, who are talking about Simulator, which is a security assessment tool for mobile communications. And spoiler, they also have hardware on board that they want to show us in the end of the talk. Welcome.
Thank you for the introduction. My name is Sebastian.
I'm Enrico.
We are both PhD students and researchers at the OTH Ringsburg doing penetration testing on IoT devices and security analysis. Maybe if you've been here yesterday or the day before yesterday, you've already seen Enrico doing other talks in that domain. So one topic we came across were security investigations on 2G and 3G communications on different IoT devices. So we always try to basically intercept traffic on 2G and later, as you will see, also on 3G to see which kind of data goes, for example, from a phone to the provider and what happens, for example, with authentication and all that stuff. For 2G, this is pretty much straightforward, as probably some of you will know, because you don't have a mechanism to authenticate your pirate base station at the user equipment. So you can basically just set up a pirate base station, and then you will have your phone connected if you configure it correctly, and everything should be fine. You can take a look at the traffic. At one project, we did some investigations, wanted to set up the 2G base station again, and we did it, it worked out, but we saw that not all the data was transferred. So the firmware of the IoT device was kind of crafted in that way that in a 2G, and it only has a 2G connection, which happens kind of often in Germany, for example, especially in trains. But then you will not get all of your data transferred to the backend. Only with 3G or 4G connection, everything will be transferred to the backend. So we want to come up with an idea of a man-in-the-middle attack also on 3G. The problem here is with a 3G authentication is that it's a little bit more complex and more secure than 2G. I mean, when I say problem, it's of course for an attacker. In general, it's a good thing, of course. The thing is, as you can see here, it's basically check it here. Here at this state of the authentication, the authentication nonce is sent from the BTS to the mobile station, and this authentication nodes gets verified. So through the verification here, the base station is authenticated. And to send the authentication nonce from the base station to the user equipment, you need some secret key that is on the one hand on the operator's base station, and on the other hand, it's also in the user equipment. When you set up a pirate base station, you will not have that secret key K, and you cannot simply extract it from a SIM card, as it's basically a secure hardware device. So our concept for a man-in-the-middle attack will be now introduced from Enrico.
Okay, so normally the easiest way to get 3G man-in-the-middle is to get a programmable SIM card, for example, from Sysmocom. You can plug this SIM card into your device. You program it with your own key, so it will only be able to authenticate to your own pirate BTS. Then the pirate BTS routes the traffic to a PC which is connected through a modem to the legitimate operator, using the original SIM card. And this works 90% of the time, even more, on most devices. However, on an IoT device which comes with an embedded SIM card out of the box, sometimes replacing a SIM card is not possible. Not because the SIM card is soldered on the board, because that's just a matter of desoldering it and replacing it with wires, but because the SIM card contains some specific files in the file structure of the SIM card that can be verified, and the modem or the device will detect in some way that the SIM card has been replaced, and it will refuse to connect. Or maybe it was just an internal error. We are not quite sure, but it's impossible to connect to our Pirate BTS using a programmable SIM card from the device we were testing. We tried reprogramming the SIM card, the programmable SIM card, but not every file is completely editable. And for example, the size of some files cannot be changed, some files cannot be deleted, some files cannot be created. So we are sad. And so what we decided to do?
Yeah, so we had to come up with another concept since our usual approach didn't work, and yeah, we wanted to continue with the project anyway, some way. So we were thinking about building the simulator or sim simulator or whatever you want to call it. So we wanted to basically replicate or clone an existing SIM card with a custom hardware, with a standard microcontroller, and with some software that we have running on the microcontroller. So when I say cloning a SIM card, of course, this is not entirely possible because the secret key and stuff like that, we cannot, as I already mentioned, we cannot extract it, we cannot clone the SIM card initially. I mean, if we could do that, we would not have to build all that software here. So we want to clone the SIM file system basically with everything except the key material. And then we want to inject custom key material that we also have in our Pirate base station, so we can somehow manage the authentication. And on the other hand, also, we have the same behavior regarding the SIM card. Everything despite the authentication parameters here. So a little bit here on SIM cards, on the protocols, just a little bit scraping the surface. SIM cards are basically smart cards, and the behavior and the protocol of smart cards is defined in ISO 7816. It's basically a simple recursive response structure. You have a class and an instruction byte, which basically gives you an idea which kind of command it is that is issued here. We will see an example later on. You have payload, of course. Then you have the length of the data or of the command itself and the length of the expected response. And yeah, for the response, you just get the raw data and some status bytes that tell you if there's, for example, more data to come or everything is all right, and you get the complete data. Just shortly on the SIM card pins, you have a VCC, you have a ground, you have a reset line and a clock line, of course. You have a programming voltage that is a pin that's basically deprecated, you don't really need it. The most interesting pin here would be the I/O, where all the data comes out and goes in. So this is where we mostly focus on regarding the SIM communication. Yeah, as we already said, SIM cards have a file system. You have this master file, as you can see in the picture, which is the root of the file system. You have directory files that are basically directories containing more elementary files. These are the EFs here, and the EFs, elementary files, are actual data where, for example, the MS-ISDN or ICC-ID, let's say, the IMSI or anything is stored. And you have identifiers that are defined per standard. When you want to query, let's say, an IMSI or something, you have to use this identifier to get it. So
since we want to create a SIM card emulator on our microcontroller, we have to implement everything that a SIM card normally does. This is the state machine of the operation inside a smart card, and the card goes from idle. It receives the header of a command, and it gets into a state where it can buy some time by sending these null bytes, which are basically a keep alive. Then when it decides that the command has to be executed, it sends an acknowledgement. Then the data is transferred in either direction, either from the SIM to the modem or to the modem, from the modem to the SIM. After the response data, after the data is transferred, the smart card can buy some more time to finalize the command by sending some more null bytes, and then it goes back to being idle. If an error happens, during the header, for example, the command is not valid, then the card goes directly from idle to this state, and then it immediately returns an error status. This is an example of a header of a command and all the parts of a command. So here there is the header of the select file. This is the acknowledgement that is sent. This is the data that is sent from the modem to the SIM card. This is the identifier of the main file. Then the SIM card takes some time to actually do the operation of selecting the file, so it will have to send keep alive null byte. And finally, it returns this 61-2A state, which basically says there are 2A hex bytes to read as a response. And then in the next packet, the next command will be get response. It gets acknowledged. The SIM, in this case, it is the SIM that is sending the data back to the interface. And finally, it sends the status, which is 9000. Everything is OK. So, this is yours.
Yeah. So for the architecture and design of the simulator, we chose an STM32F103 for the low layer communication that basically does, the, let's say, low layer, hardware layer here, and the JavaScript for the driver that simulates the actual file system on the higher layers. I mean, the thing was, this was just a part of a bigger project. It was not like that we say, okay, let's build the simulator and we decide to do that and that. It was basically just, we had a problem in a bigger project and then we said, okay, we need something to solve it. So we built a simulator and we used hardware that we had laying around and basically JavaScript because we think it's good for rapid prototyping for us here. So the microcontroller is good because we don't need to code any drivers on our own because the STM already works out of the box as it is a USB CDC serial device. It is super cheap. We had it just laying around in the lab, and it has UART interfaces that can be configured to work basically as pins and as ISO 7816 cards or interfaces. So what you see here is the first prototype of the simulator. We just used a breadboard and stick everything together to the pins and attach some connector for the SIM card. The bill for the material here is around 20 euros roughly. The second picture here is our super professional prototype that's basically production ready. We have some LEDs attached basically for debugging, and it's everything a little bit more nicer looking and a little bit more stable, so not all the cables come off when you have to sneeze or anything. So a little bit detail on the software. We have a Node.js application. We have the SIM file basically defined in a very, very big JSON file. So it's like something like a huge dictionary where all the files are specified. We have already inside the code some example SIM cards that we used in our projects and that we had laying around, or for example in our phones. It can be easily extended to support more SIM cards if you just want to basically code the file system in the JSON. You can check that the emulation works as expected because it can be unit tested. We have some test files inside. And with that, we achieved our goal that the modem, the actual IoT device where we did the investigations, cannot distinguish between the emulated card, which would be the STM hardware here, and its actual embedded SIM included. So this is what we wanted. So actually, let's say achievement unlocked here. So we are happy right now. Right?
Yes, it works, but it's extremely painful to create a virtual SIM card this way. It takes a lot of time. So the whole file structure, as you said, has to be defined in a JSON file, and there are a lot of files in a USIM, in a modern SIM card. And even though, we wrote this script that automatically does a unit test, let's say it creates a unit test out of a SIM card log. So from an original SIM card log communication, we can automatically make sure that everything our virtual SIM card does is exactly the same as the original SIM card. However, we have to write this huge JSON file for any new card that we want to support.
So we came up with another idea to basically get rid of all that huge work. So it's another man in the middle, but regarding the SIM here. So what we do is we forward all the APDUs, the packets that are the commands from the ISO 7816, from the modem to the original SIM card. And then we only want to trigger our simulator on the authenticate APDU, because that's the only thing where the key material is involved. And besides that, we are anyway cloning the SIM anyway. So we are using the original SIM completely. We just forward the APDUs, and only on the authenticate APDU, which does the authentication, we are spoofing a response using the simulator. This gives us the opportunity of not having to the whole file system in a huge JSON file. So which kind of use cases would you have with the simulator? You can do penetration testing on modems. You can see what's going on there. You can also do unit testing for any application that has somewhat to do with smart cards. Security investigations, of course, on SIM cards and smart cards are possible, and on 3G communication, as it was the intended use actually. Also, another use case would be relaying a smart card over a long distance from the actual reader.
You've got 1 minute left if you want to show your device.
Oh, 1 minute.
Okay.
Okay. So.
Yeah. Okay.
So yeah, we have a video ready, but I thought we had more time.
We are talking 60 minutes right now. Anyway. Okay.
Okay. So first of all, this is 3 terminals, debug window, HLR from the Pirate BTS, and the actual simulator window. This is in this case, we're showing it to work with a phone, not in man-in-the-middle mode. This is just a phone connected to the simulator, and it has a virtual SIM card running.
Just let it run, and we don't have time anyway, so just let it run.
Yeah, the phone is turned on. At this point, it will start communicating with the SIM card very soon, and we have, these are all the APDUs, all the packets that are being transmitted between the SIM card and the phone. At a point, this will boot, the phone will boot. However, it will still not attach to the Pirate BTS, because in this demo, we were not spoofing the MNC and MCC and all the parameters from the BTS. This was just test network. So it will hopefully, it's fast enough. Okay. So here there is the phone complaining about not being able to connect to the BTS. Okay. So now the phone will look for every network in the area. Oh, and here I skip to the important part. But here, if I select the test network, the HLR will receive the authentication request in the upper right corner here. The phone connects. It has a 3G connection, as we can see from the zoom here. You can see there was a H in the upper right corner. And if I open man-in-the-middle proxy and I visit some web page, I can show that, the 3G man-in-the-middle works using a completely virtual SIM. And that's it. It's available on GitHub. References? Questions?
We are pretty much on time.
I thought we had more time.
Okay, we got time for 1 or 2 questions. No question at all? Okay, one question from my side. Does this give you the ability, I mean, you mentioned penetration testing as a possible use case. Does that give you the possibility to simulate some specific attack that you aren't able to perform with a normal SIM card or only virtual SIM card?
Well, for example, any fuzzing attack on the actual SIM interface, that could be a use case, yes. So, for example, you could inject APDUs that are unexpected, or, for example, send some file over the select file command and read binary, send some file, and then immediately after change it many times and see if the modem gets confused in some way. So definitely it's possible to use it for fuzzing.
Okay, thank you. Any further question? Okay, if this is not the case, please thank our speakers.